We're going to talk a little bit about different types of wave interference. So right off the bat, let's make sure we understand what we mean when we say interference. This is basically when we have two or more waves that come together, and the combination of those waves are going to temporarily change the amplitude of the resulting wave. So this is basically anytime we have multiple waves in the same space, at the moment that they're amplitudes overlap, then we're basically going to do the math with those two amplitudes, and the resulting math will either be that they have added together for a larger value, or they are subtracting for a smaller value. So there's four specifics that we're going to be discussing: constructive and destructive interference, just kind of in general, resonance, and standing waves. So constructive interference, hopefully we're all comfortable with the word to construct, the root of this word construct, which basically means to build, to put together, to create some new larger thing. So it says that when we have two waves that meet and combine, they temporarily form one large amplitude. So this would be whenever the amplitudes of our waves that are mixing together are both on the same side of equilibrium. So we have two positive amplitudes, or we have two negative amplitudes. The fact that it's positive or negative does not determine whether or not it's constructive or destructive. It's if both of the waves are on the same side of equilibrium. So they're both positive amplitudes or they're both negative amplitudes. That's when they're going to combine for constructive interference. So I have an illustration here for you. We have two waves. This is wave one. Oh, let's change that color. And this wave is moving to the right. And let's say that it has an amplitude of a positive 1. It's a positive value for the amplitude because it would be on the positive side of equilibrium. And then let's say that wave 2 is this wave right here, and it also has a positive amplitude of 1. So you can see in the illustration that these two waves are moving towards each other. So eventually they're going to meet up, and at the moment where they meet up, those two waves are going to join together. So we have a positive amplitude 1 from the wave on the right. We have a positive amplitude 1 from the wave on the left. So at the moment that they overlap, they are going to constructively interfere to give us an amplitude of a positive 2 meters at this moment. And then you can see from the illustration, they're going to continue moving after that moment in their original form or at their original amplitude. Again, this can also happen if your two waves are on the negative side. So if we had wave 1 had a, let's make that a negative 1, and let's say that wave 2 has a negative 2 value, then when these two things meet up in the middle, we're going to have this negative 2 and that negative 1 that are going to join up. So our resultant amplitude here would be a total of a negative 3. And then they would continue moving along their routes undisturbed. It's just for the moment that they're occupying the same space at the same time. Okay? All right, so let's look at destructive interference. Destructive interference is when our waves are on opposite sides of equilibrium. So in this case, we're going to easily be able to identify destructive interference because we will have one positive amplitude and one negative amplitude trying to mix together at the same time. So you see I have two different illustrations here. The first one is showing complete, total destructive interference. So in this first example, we have a positive amplitude of 1, and we have a negative amplitude of 1. So if we do the math on that, plus 1 minus 1 equals 0, right? If we think about this as something tangible, something that we can maybe visually understand or experience a little bit better, then let's think of this as our green amplitude here, our negative amplitude. Let's think of that as being like a hole in the ground. So we've dug a little trench, or we have some sort of hole, some sort of missing soil compared to ground level, right? And then let's say that this purple amplitude over here on the left, our positive one, is a pile of dirt. Well, if we take this pile of dirt and we put it into that hole in the ground, then if it's exactly the same amount of dirt that's missing, then it's going to perfectly, completely fill that hole, and we're going to end up with a nice level ground surface, right? Well, that's essentially what happens when these two waves combine, because we have the -1, and then we have our +1. So if we put that +1 on top of the -1, they completely perfectly overlap. So we end up with 0 amplitude. So there's no amplitude at that moment. So this is where two waves completely perfectly cancel each other out. And yes, this does actually happen. Again, it's momentary. It's only at the moment that they are perfectly overlapped, occupying the same space at the same time. But it doesn't always happen this way. If you look at this illustration over on the bottom right, this is showing you partial destructive interference. So here, they gave us some nice little graphing space here so that we can see the values of these waves. It's drawn a little differently, but it's the same idea. So here we have a wave, which according to this illustration would be a +1. And then here we have a wave, that would be a -1. Oh, and you know what? I thought this gave us 2. Let's make this a -2. Okay, let's make this a -2. I thought this was partial, but this is total. That's all right. So if this is a -2 value, and this is a +1 value, then when they overlap, we would have our -1 overlapping with the +1. So the +1 is going to fill in this space, but that leaves us with the remaining negative, right? +1 minus 2 leaves us with a -1. So our resulting wave here would actually be this -1 value. And so that would be an example of partial destructive interference. Here are some additional examples so you can see some more illustrations of interference. We have examples of both total and partial destructive interference. We also have some examples of constructive interference. I wanted to show you this illustration right here though real quick. So this is what we would call a beat pattern, or this is how we would obtain our beat frequency. You can see from this illustration that unlike the other examples that we had, our waves don't necessarily perfectly overlap. So if we look at our picture and if we find just any specific moment here, I have a positive amplitude right here, and at this same moment I have a positive amplitude, and they are both perfectly overlapped, right? So that's perfect constructive interference. But if we look at one of these spaces in between, so I have a positive perfect positive amplitude here, and then if I look right underneath that, we're a little bit destructive because parts of that overlaps on the negative side and part of that overlaps on the positive side. So if we look at our illustration below, this green line represents our resultant wave, the resulting amplitude because of the interference that the waves experience. And you can see that the green line here, I know there's a lot going on this picture, but the green line changes because depending on whether these waves are perfectly in phase or not determines how well they overlap and if we get constructive or destructive interference. So if you're asked a question about beats or beat frequency, our beat frequency is basically the frequency that represents the difference of our two waves. So let's say, for example, this first wave has a frequency of 202 hertz. And let's say that the second wave has a frequency of 208 hertz. Then the beat frequency is just the difference between the two. So our beat frequency, or our resultant frequency, we would just subtract. 208 minus 202 is going to give us 6. So the resultant wave, the beat frequency, would be 6 hertz because that is the difference between those two individual frequencies. All right, next let's talk about resonance. Resonance is a concept where we have multiple waves of the same frequency, and basically what happens is they line up so that they are perfectly in sync. So it's nothing except complete, total, constructive interference. So the wavelengths and the frequencies are the same because it's actually multiples of the same wave, exact same sound, exact same wavelength. And they're just perfectly overlapping. So the only thing that's going to change is going to be the amplitude of that wave. And so as a result, and if you recall from the first set of notes that you guys had, amplitude corresponds with the intensity. So specifically, if we're talking about sound, if we increase the amplitude, we're increasing the intensity, which normal people would just say we're increasing the volume. So as a result of resonance, specifically with a sound wave, we get a louder sound. So if you have heard of some of these examples, so obviously pushing someone on a swing, that's not a sound wave, but I've used the example before of somebody moving on a swing and how that kind of shows that oscillating motion, how we go back and forth. Well, if we have somebody applying that force so that we're perfectly in sync with our original swing pattern, then every additional swing, every additional restoring force is going to simply increase that amplitude or allow us to swing higher and higher if we're physically on a swing, right? Perhaps you guys have heard of myths, and there's actually a mythbuster out there that I really love called Breaking Glass. But you've probably heard of singers who have been able to actually shatter glass with their voice. This would be an example of resonance. The idea here is that every object has its own natural vibration pattern. And so we call that a natural frequency. So up here in this definition, the natural frequency. So in other words, if you were to take a wine glass or if you were to take a piece of glass like on a window and thump it, it's going to vibrate. Whatever that vibration pattern is, that would be its frequency. Well, if we have somebody who has the ability to control their voice such that they can actually create a sound wave that matches the same frequency that wine glass or that glass window vibrates on its own, in theory, what we do is we simply create the sound with our voice. That sound wave applies the force to the wine glass or to the glass window and causes it to vibrate. And so once that object begins vibrating, as long as they can create that sound wave at exactly the same frequency, resonance takes place, which is where you have multiple waves of exactly the same frequency that just build up and build up and build up. And all it does is create a really large amplitude. And obviously, glass is not meant to be flexible. So if they can produce that sound wave to be strong enough, forceful enough, intense enough, that amplitude becomes so large that the glass eventually breaks. So that's what the theory of being able to shatter glass with your voice is all about. But really, it is this vocabulary word resonance. That's really all it is, okay? And yes, FYI, it is possible, although it's really, really difficult. All right, the last thing we want to discuss with you is a standing wave. So a standing wave is basically where you have one wave, but it reaches some sort of fixed boundary. So in the Slinky lab or the Wiggler lab, we have a person holding the other end of the Slinky, which serves as our fixed boundary. So the wave goes down the Slinky, hits the stationary hand, and then bounces back towards the original sender. In the Wiggler lab, we have a vibration that takes place or a wiggle that takes place on one end of the string. It travels down the string. It meets the top of the pole where it has been attached or tied down. That serves as our fixed boundary. And then that wave reflects and goes back towards the original end that was wiggled or where the vibration came from. So if we look at this illustration, the yellow line here represents the original wave. So in real life, the wave comes down the string like this. But then once it hits that wall, that energy is not completely absorbed by the wall. It doesn't just stop the wave. It actually hits that wall, and then that force is applied back onto the wave, and it causes that energy to travel back in the other direction. But what we see here is that when that energy gets returned, it actually comes back inverted. Now, we would describe this reflected ray or wave as being the same frequency and the same wavelength. So you can see from the original picture, they perfectly overlap. But what we have is a mirror image, okay? So we say that it's reflected and inverted. It's reflected because it's sent back identical to the original, except that it's inverted, meaning that it turns upside down. And so when this happens in real life, typically that wave is reflected back, and because of the actual frequency and energy of the original wave, it comes back so fast that to our human eyes, it's too quick for us to keep up with. And so it ends up looking like we have this little bubble. So this picture right down here is showing you what we would see. We would actually see as if the string is present on the top and the bottom at the same time, which we know is not possible. It can only be present in one place at a time. But the frequency is so great, the vibration pattern is so fast that our eyes can't keep up with that. And so we end up seeing a high and a low at exactly the same time. In actuality, the string is only in one place at a time, but we're seeing that reflected in inverted ray. So we end up, or wave, sorry. So we end up with this pattern that we call a standing wave, okay? So this illustration right here is an illustration of a standing wave. This part of our picture right here is an illustration of a standing wave. And so we would identify the parts of the wave as being nodes and antinodes. The nodes are going to be these locations here where we have zero amplitude, or using our vocabulary from today, this would be complete destructive interference, where we have a resulting amplitude of 0. And then our antinodes are going to be these highs and lows. Now, when we go to count them, remember, the string is only physically in one place at a time. It's not actually in both. So we would say that this particular illustration would have 3 antinodes, and then our nodes are going to be here, 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 and here. So we would have 4 nodes in this particular illustration. Okay, so this is a standing wave. Again, it is when a wave hits a fixed boundary, is reflected and inverted, and we end up with this illustration. The areas of maximum amplitude, our highs and lows, we're going to call our antinodes, and the areas here where we have 0 amplitude, that's going to be our nodes. Okay, so this was just a brief overview of some wave interference. Oh, I'm sorry, there's one more slide here that we would need to go over. Harmonics for my musicians. You probably understand what this means pretty easily. So this is basically what we're going to see when we hear those different notes in our music or with sound. So harmonics are basically multiples of that initial, or what we're going to call our fundamental wave. And really all I need you guys to know about this is that if we know the frequency of our first wave, it's called the first harmonic, or it has the special name of the fundamental for that first harmonic. Then every note after that, every harmonic after that is just going to be multiples of the first. And so you can see from the illustration, I've kind of given you an example where if we knew the frequency of the first wave, then we could then determine the frequency of the fundamentals of that wave. All right, I hope this was helpful. You guys have a great day.